So, p-series, also called hyperharmonic series, are the summatory of 1 over n to the p when n starts at 1 and goes all the way up to infinity. And it only works for numbers that are amongst the natural positive numbers. So, moving on. The infinite series converges to a real number if the improper integral, meaning the limit of the definite integral, is finite, meaning it stops at a given number. So, if the integral diverges, this series diverges as 2. This is what we call the integral test of convergence. According to this test, if p equals 1, the harmonic series diverges. If p is bigger than 1, it's an overharmonic series and converges. And if p is less than 1, diverges. Also related to this, we have the natural logarithm series, and it's the summatory of 1 over the natural logarithm of n to the p. In which case, if we apply the same integral test of convergence, we have that p being less than 1, it diverges, and p being more than 1, it converges. In taking into account two specific cases of this p-series, we have n equals 2 and n equals 3. So, in the first case, it's called Bessel problem, and it's the summatory of 1 over n squared, where n starts at 1 and goes all the way up to infinity. And taking the limit of this, we have that 1 over 1 squared plus 1 over 2 squared all the way up to 1 over n squared, where n equals infinity. It's 1.6449. The second example, is when n equals 3, and it's called the Apéry's constant, and also called theta, equals the summatory of 1 over n to the cube. And taking the limit of this from n to infinity, we have 1 over n cubed plus, 1 over 1 cubed plus 1 over 2 cubed, etc., up to infinity. And that number is 1.20205 approximately, because they're both the Bessel problem and the Apéry's constant, they're both irrational numbers. They're both very complicated numbers. But approximately it's 1.64 and a 1.2020.
Welcome. Today we're going to talk about the limit comparison test. This test is meant for two series to know either if they converge or if they don't converge. And its statement is as follows. So, the sum of n, an. Suppose that you have two series, and these series are the sum of n, an, and the sum of n, bn, with an and bn bigger or equal to 0 for all n, for all values of n. Then, if the limit of n towards infinity with the first series over the second series equals c, with c bigger than 0 but smaller than infinity, then both series either converge or disconverge. Now, how do we know that? We'll tell in just a second. So now we're going to solve our first example to determine whether this specific series converges or not. So we're going to take this series and we're going to compare it to the next series. We're going to compare it to this series to determine whether it converges or not. So we know that this series converges because we could take out this 5 over 2, and just as if it was an integral, we'll have this 1 over n to the square. So we know that this specific series converges. So by comparing the original series to this one, we'll know if these series converge, because if our limit test results, then both series must converge. So now we're going to follow the statement of the limit comparison test and take our original series and divide it by the series we want to compare it to, which will be 5 over 2n squared. Now we can flip this and multiply it, so it will be like this. The purpose of this is to have the same power in the denominator and in the numerator. So we're going to have this. So now what this test tells us is that if the power of the numerator is equal to the power of the denominator, then the limit is this, is 10 over 10, which in this case equals 1. Now we know that these series converge. So this specific series, our original series, by the comparison test, we know that it also converges. So for our next example, we have this series. Now we're going to take these two factors, and we're going to have 3 over n over 4, which will be equal to 1 over n. And we'll want to compare this series to this one. By the way, this series, it diverges. It does not converge. So we have this series which diverges. By comparing this divergent series to this one, we'll know if the first series diverges or not. So once again, we apply the statement. Which will give us this, our first series over our second series. Once again, we'll flip and multiplicate. So we have this. Now we apply the multiplication. We'll have this. So once again we apply this, that they have the same power, the numerator and the denominator, which means that this limit will be, in fact, once again 1 over 1, which is 1. So since this one is bigger than 0 but less than infinity, it means that both series diverge. So both series diverge, and that proves this test.
I'm going to explain D'Alembert's ratio test, who basically consists when you have an n in the equation, you can replace it with an n plus 1, and then you have to divide it by the original function. So in that case, a to the n it's equal to a n plus 1 over a to the n, a n. And we have 3 cases. In case 1, if the limit n goes to infinity of the absolute value of a n plus 1 over a n, if the result is less than 1, the series are convergent. In case 2, if limit of n goes to infinity of the absolute value of a n plus 1 over a n, if the result is higher than 1 or infinity, the result is divergent. The series are divergent. In case 3, if the limit of n goes to infinity of the absolute value of an plus 1 over an. If the result is 1, it's an incomplete result. So now I'm going to explain some examples of some of the cases. So in this case, the sum when n times minus 4 to the n over 3 to n minus 1, we have that the limit when n goes to infinity of the absolute value, this represents n plus 1. So we are going all n's will replace it with n plus 1. So we have n plus 1 times minus 4 to n plus 1 over 3 n plus 1 minus 1. And this will be divided by the original function, that is n times minus 4 to the n divided by 3 to n minus 1. Now you can see that I'm multiplying instead of dividing. That's because I use the inverse. So that I invert those numbers, so I can multiply now, and then I'm going to simplify these terms. So I have minus 4 to n plus 1, and I have minus 4 to the n, but I can eliminate this part and this part, and it's going to be a 4 only, because I have n plus 1, and then I have 3 to n plus 1 minus 1, and in this side I have 3 n minus 1. So I can eliminate the n, the minus 1, and this. So now I just have a 3 to 1, that it's 3. And that's equal to the limit of when n goes to infinity of the absolute value of n plus 1 over n times minus 4 over 3. And then I can take out the minus 4 over 3, but it's going to be positive. So I have 4 over 3 when the limit of the limit when n goes to infinity of the absolute value of n plus 1 over n. So when I have a rule of the rational function, is that if the power on top is the same as the power on the bottom, I just need to analyze the ratio of the coefficient. So I have a 1 and 1, and that is going to be 1. So I'm going to have finally 4 over 3 times 1, that is 4 over 3, and that number is bigger than 1. So we can conclude that the sum of n times minus 4 to the n over 3 n minus 1 is divergent.